So now we're just going to go into a little more detail for balancing chemical reactions. Okay, so we're again given an unbalanced reaction. This is just a little bit of a summary of stuff we covered in the previous lesson, but it's just kind of summarizing that. So the subscripts, those small numbers, tell us the ratio of different atoms in one molecule. So for example, if we look at this molecule here, methane, we can see that there is 1 carbon atom and 4 hydrogen atoms in each molecule of methane. Now the warning I have for you is that when you're doing these stoichiometric calculations on exams, a lot of the times your profs may give you unbalanced equations and they're not going to remind you to balance them. Okay, so you'd be then expected to balance them, and we said that you have to balance them in order to get any calculation right. So that's going to always be the first step. Okay, so let's balance this equation too, just for extra practice. So right now I have 1 carbon on the left, 1 carbon on the right, so carbon's fine. I have 4 hydrogens on the left and 2 hydrogens on the right. So I'm going to put a 2 there. So now I have 4 hydrogens on both sides. For oxygen, I have 2 oxygens on the left, and on the right, I have 2 oxygens plus another 2. So in total on the right, I have 4 oxygens. So in order to balance that, I'm going to want to put a 2 here. So now that I'm doing 2 times this 2 to get a total of 4 oxygens on both sides. So this equation is now balanced. Now I just wanted to share with you guys some more detailed steps on balancing chemical reactions. I know some of us learn better when we see things in writing, so I wanted to put it in writing for you, but as you can see, balancing chemical reactions is pretty straightforward, so you don't have to memorize these steps or anything, but I think it still is helpful to go over some of these tips as they'll help us, especially when we're dealing with more complicated problems. So one thing I find helpful is that for more complicated problems that we'll look at soon, it helps if you try to balance the element that only appears once on both the reactant side and the product side. So for example, let's say you see a chlorine atom. It just appears once on the left side and once on the right side. Start with that chlorine atom. It's not a very common atom, so starting with that would make it easier. And we don't want to start with oxygen, something like oxygen or hydrogen, since there's going to be so many of them, and that's usually going to be the thing we balance last. Okay, the next thing is when we see a polyatomic ion. So we're actually going to review this in just a couple of lessons, but polyatomic ions are pretty much when we have certain atoms that they like to kind of be in a group together. You can think of it as, so one example of one is nitrate, NO3-. Okay, so when you see certain polyatomic ions, and I'll show you a table with those in it, make sure you're treating the polyatomic ions as one thing, so as one nitrate ion rather than 1 nitrogen and 3 oxygens. It's going to be a lot more complicated to balance, and it's just way more easier if you focus on identifying any polyatomic ions you see and balancing them by looking at, okay, there's 1 nitrate on the left side and 1 nitrate on the right side, so it's perfect. Okay, and we'll see an example of that. So then you just want to balance all other elements, which we've seen. And again, it's a good tip to start with the least common elements that you're seeing to the most common elements. So most common being like oxygen and hydrogen, they're going to usually be present in the equations a lot more. And then how do we know when we're done and we have a good answer? Well, you want to make sure that your coefficients are all whole numbers. We don't want to see any fractions. If you do, for example, see a fraction like 7/2 oxygen gas, let's say that's in your reaction, you want to get rid of that fraction, and you would just do that by multiplying by the denominator. So here the denominator is 2. I would multiply by 2 so that it could cancel out, and you'd be left with 7 oxygen. Just keep in mind, if you ever do this, whatever are the other parts of your equation, so I'm just calling the other molecules C and D, if I multiply one thing by 2, I have to actually multiply everything by 2. So whatever numbers these are in front of the other molecules, you'll also have to multiply those by 2, just something small to keep in mind. The last thing is you want the simplest integer ratio possible, or in other words, you want to have the lowest numbers in your balanced chemical reaction. So let's say, let's use the A, B, C, D example again. And let's say all of these are 2. So I balanced it. I think I got a good answer, but they're all 2. That can actually be simplified further if I was to divide each of those by 2, since 2 can go into every single one of those. And I'm going to be left with my better answer, which has the smallest possible numbers with just coefficients of 1 instead. So if there's ever a way to simplify the numbers where we can divide all of them by the same number to get smaller numbers, you want to do that because that's how you get the correct balanced equation. And the last step is just you can check your answer to make sure that it's right. Okay, so this is the equation we already balanced. One thing I'm pointing out here are stoichiometric coefficients. So that's just a term that's referring to these numbers we see in the front of each molecule. So here, for example, it's telling us that in this equation we need how many oxygen molecules for each methane molecule. So for each methane molecule, methane's on the left, we're going to need 2 molecules of oxygen. And for each methane molecule, we would produce how many water molecules. So for each methane that's consumed, we're going to produce 2 water molecules. Okay, stoichiometric coefficients also tell us about the ratio of moles needed. So for every 1 mole of methane, we would produce how many moles of carbon dioxide. So if you have 1 mole of methane, you're going to get 1 mole of carbon dioxide, since there's just nothing written there. So it's, we say that it's like an invisible 1. So you're getting 1 mole of carbon dioxide. And again, so we did go over this, but it's just reminding us that the concept here to remember is that when we're balancing equations, make sure that you're multiplying coefficients by subscripts to see exactly how much of an atom we have on each side. By that I mean, if I need to figure out the number of oxygens on the left side, I'm going to want to multiply the stoichiometric coefficient from the balanced reaction with the subscript, so I know that 2 times 2 is 4, so there are 4 oxygen atoms in total on the left side here. Finally, I just wanted to show us a quick example of how you can simplify a reaction to make sure that you get those lowest possible coefficients we talked about. So let's say I balanced an equation and I got these stoichiometric coefficients. Do you think those could be simplified further? So yes, they could be. So what number do you think I'd want to divide each of those stoichiometric coefficients by? So I would not want to divide by 4 because 2 over 4 would get me 1/2, and again, I don't want fractions. But I would want to divide by 2 since 2 can go into each of those numbers. It's the largest number that can go into each of those. So if we're going to divide by 2, you're going to now see the new coefficients. So 2 divided by 2 is 1, 4 divided by 2 is 2, 2 divided by 2 again is 1, and 4 divided by 2 is 2. So now this is actually our correct balanced equation with the lowest possible coefficients.